Today's topic of discussion is fluoroform or CHF3. So this is a pretty interesting molecule. I would say this is the first member of the haloform series, but generally we ignore discussion about this molecule because its chemistry is little different. So we shall learn that thing. So today's topic of discussion will cover few points like preparation, acidity comparison and trifluomethylation. But before going to detail, student, I want to give you one suggestion that please visit the description box of every video of my channel. So actually I upload the related lectures link there. So not only this, I shall discuss one MCQ too during this video. So let's first go to the MCQ. So what is the major product of these reaction? You can see. So 4 options are provided and one of them is the right answer. I request you student, please pause the video, try by yourself and write few words as explanation about your answer. And don't worry, at the end of discussion you will get the right answer. So let's go to the main topic of discussion, that is fluoroform. Okay, so you can see this molecule, it is actually a tetrahedral derivative of methane. You can consider where 3 hydrogens are substituted by these 3 fluorine atoms. And this fluoroform, if you look at it, is actually a side product of Teflon manufacturers. Now, it's actually a low boiling liquid, it's non-toxic, non-ozone depleting gas. However, it is actually a potent greenhouse agent. So this is the difference, please remember this point. And there is actually great interest method of use of this gas as synthetic reagent. Why? For trifluomethylation reaction using trifluoromethyl anion, which could easily be prepared from this. I shall discuss at the later, because this is a very interesting molecule for CF3 group introduction. Not only that, it can undergo fluoride elimination to produce difluorocarbon. That's another interesting thing. We'll learn slowly, step by step. Now, so first let's go to the haloform reaction. So, and we'll learn what is the difference, why we can't prepare fluoroform using this method. Generally, whenever you see haloform reaction, this picture comes in front of you. That it is written if you have a ketomethyl compound or a secondary alcohol, I mean RCHOH-CH3. So, if you treat these with halogen or base like this chlorine, bromine, iodine or corresponding hypohalite salt, I mean NaOX, if you treat them with this reagent, they produces 1 carbon less carboxylic acid sodium means salt. Since if you take sodium hydroxide, then it will be sodium salt, and not only that, along with that it produces haloform. And if you take chlorine, then it's chloroform. If you take bromine, it's bromoform. If you take iodine, it is iodoform. This thing we know, but that time it is explained that X cannot be halogen or fluorine, means X cannot be fluorine. Now question, why can't we prepare fluoroform using this haloform reaction? For that purpose, you need to understand the unique chemical reactivity of fluorine. Student, it is the most electronegative atom in the periodic table and it is one of the most chemically reactive. So when I say the word most reactive, automatically one word indicates that it is less selective. This haloform reaction is actually a selective reaction because it will react only with these methyl or these methyl, but it will not affect others. But this fluorine, since it's most reactive, it is less selective, so it is very difficult to use. So that's why this method is not useful for fluoroform using like fluorine and sodium hydroxide. You may consider like that. And if you ask that, sir, NaOF can I use? See, this reagent has a difficulty. Although I haven't seen it, I have doubt whether it exists or not. Because in case of NaOX, if you look at here, the oxidation state of this halogen is +1. So it is oxidizing in nature. But if you look at NaOF, the oxidation state of this fluorine is -1. That's why reactivity pattern is also different. Why? Because fluorine is more electronegative compared to oxygen, so that's why this is -1. And if you compare oxygen with other halogens like chlorine, bromine, iodine, oxygen is more electronegative compared to them. So that's why in this case the halogen carries these positive charge. Okay, I believe you have understand the story that why can't we prepare fluoroform directly by using haloform reaction. But isn't there any way? Don't worry, when there is a problem, scientists always try to find out solution. So here the solution. Solution is Swarts fluorination or Swarts reaction, because student, we have previously learned in class 11-12 also that if you treat methyl bromide with silver fluoride, it's actually this silver fluoride is student ionic compound. Okay, so what it can provide? It can provide F minus. So what this F minus can do? F minus can attack here and this Br can leave. So in this way it will produce CH3F and silver bromide. Question, why? Fluorine is not a good nucleophile. We know fluorine is a mild base, but it is not at all a good nucleophile. But this reaction happens because the silver loves bromine and it form a covalent compound type, means silver bromide, which got precipitated out from this reaction, and that is the driving force for this reaction. Okay, because silver bromide is coming out from the reaction mixture, so according to last atelier principle, equilibrium will shift towards the right side, means product side, and consequently fluorohydrocarbon or fluoro derivative will be produced more here. Okay, so this Swarts reaction is actually a general reaction strategy for halogen exchange with fluorine. Please remember. Now in this case, reagent is silver 1 fluoride or silver fluoride, mercurous fluoride, mercury oxidation state is 1, cobalt 2 fluoride or antimony trifluoride. These are the reagents. Now one information, student, I suggest you please remember that silver fluoride is water soluble. It's ionic compound as I told, but silver chloride, silver bromide and silver iodide, they are water insoluble. Sorry. So you may ask that, sir, why it is water insoluble? So for that purpose, you need to understand the covalency in this silver chloride, bromide and iodide, but ionic nature with this fluoride. Student, one question for you. I suggest you all to try in the comment box. Why calcium fluoride is insoluble? Although calcium chloride, calcium bromide, calcium iodide, those things. So this is your question. Previously, actually, if you look at here, student, we have prepared methyl fluoride, but it is not still the fluoroform. Question, how can you prepare fluoroform using this Swarts reaction? So if we treat iodoform, so this is actually iodoform with silver fluoride, it will produce fluoroform plus, not silver bromide, it is silver iodide. Okay, it will be precipitated out. It's true. Now I understand. Now this reaction is actually, student, violent reaction, extremely exothermic. So when there is a chance of accident, there is a risk factor, scientists try to modify this. Now how this thing is modified? Because this 3 means silver iodide is a very stable complex, it reacts, it produces energy, and remember another thing, CF bond is one of the very stable covalent bond, and here 3 are forming at a time. That's the issue. So that thing is handled by modifying this process into 2 steps. The first step is associated with reaction of bromoform CHBr3 with antimony trifluoride. In this way, student, 2 bromine atoms are replaced by fluorine. So CHBrF2 produced. Now in the next step, this CHBrF2 is reacted with mercuric fluoride. This is a modified method. You can get these reference in this paper. So this mercuric fluoride, and it produces this fluoroform, and bromine is gone with the mercury. Now this is the way to prepare fluoroform under milder reaction condition. Now another method if we discuss, because mercury, you can think that, sir, still toxic thing. Yes, it could be avoided, because in modern days people doesn't allow to use toxic reagents like mercury. If there any alternate method where we can avoid this step, that is highly appreciated. Okay, so let's learn another method for this preparation. Here this is actually, you may consider it's a proton exchange reaction. This is a CHBrF3, and in this case the bromine is replaced by hydrogen which come from methane. So this bromine goes to methane and this hydrogen goes to this carbon. In this way it produces CHF3 and along with that methyl bromide. But this reaction requires pretty high temperature, 873 Kelvin, and actually this catalytic reaction of methane with this trifluorobromomethane over cobalt, copper or manganese JSM5 zeolite catalyst. Simple removal of halogen, so debromination and attachment of hydrogen. So this is the reference of this literature. But the most interesting method for preparation of this chemical or industrial method for these bromoform is this reaction, where chloroform is treated with HF and which produces fluoroform and HCl. Now you may have a question that, sir, we know that chloroform could be prepared very easily by haloform reaction, chlorine, sodium hydroxide, cheap chemical. You can prepare, no problem. We use huge amount of this thing even in laboratory reagent also, it is cheaper. Now why this HF will react with chloroform? Because as I told, fluoride is not a good nucleophile. Not only that, HF is not that much acidic. It is a weakly acid because this HF bond is strong too. So question, why this reaction happens? For that purpose, or what is the driving force for this reaction? So for this purpose you need to understand the nature of the product. CHF3, actually 3 CCl bond is replaced by 3 carbon fluorine bond, and remember these carbon fluorine bonds are one of the strongest covalent bond. Remember student, this information is highly useful to learn fluorine chemistry, and this is one of the fluorine chemistry related lecture. Previously I uploaded many, you will get the links in the description box. This is a very strong bond, so huge amount of energy is expected to release. So that is actually the driving force for this reaction. So stable bond formation is the driving force. Now in the next step, if you look at, that is acidity comparison between chloroform, fluoroform. So who is more acidic between chloroform and fluoroform? So student, remember one rule. If anywhere question asked about acidity, you should focus on the conjugate base or CB. Okay, what is the conjugate base? Just remove proton, means H plus, from this molecule, and whatever thing will be produced, that is called the conjugate base or CB. Now if the conjugate base is more stable, means the anion is more stable, then the compound will be more acidic. That is the simple logic. So if you remove the proton from this fluoroform, what do you expect? That it will be an anion. You may consider such CF3 minus trifluoromethyl anion. So you can represent this in a two ways. You can either represent in this way, so you can indicating that it's a hybridization sp2, or you can say that's a no, not this, it's sp3. Now generally carbon ion changes its hybridization because it was actually sp3. So from these it changes its hybridization because such that the negative charge could be delocalized, but in this case that thing is not that much possible. Why? Because this fluorine also has lone pair. Now you will say that, sir, fluorine is strongest electronegative atom, it has a very strong minus I effect, sigma withdrawing. I agree. By that it somehow stabilizes this negative charge through sigma withdrawing, and that thing could be done either by sp2 or sp3, both ways. But if you look at this, so these negative charge, this actually negative charge means it's a pair of electron, or more specifically if I say it's a lone pair. So these lone pair could have a repulsion with the lone pair of this fluorine. So that's why there is a significant amount lone pair repulsion. So this is actually a destabilizing factor. I agree student, minus I or sigma withdrawing is a stabilization factor. Compared to that, there is a unstabilization or destabilization factor because of this lone pair on this fluorine atom. So based on that we can say that okay, this conjugate base, it is not that much stable, it's actually moderately stable. However, if you look at this chloroform, it produces CCl3 minus. Question, Similar logic is true for this, but it has another unique point of stability. What is the stability? So this chlorine has energetically accessible vacant d orbital. I repeat the statement, energetically accessible vacant d orbital. So that's why it can accept electron density, pi electron density from the carbon ion 2. This negative charge. So in this way you can see that this negative charge could be delocalized into the vacant or d orbital of chlorine. It is true that the sigma withdrawing or minus I is there. It's true. Not only that, minus R also work because of this vacant d orbital. And remember, fluorine doesn't have any vacant d orbital because it's a second row element, or 2p doesn't have corresponding d or 2d. So that's why the negative charge is more delocalized in case of chloroform. If I say more delocalized, it is more stabilized. So that's why chloroform is more acidic. Student, chloroform is more acidic than fluoroform, and experimentally if you look at the pKa value, the chloroform pKa value is 15.7, but if you look at the fluoroform, its pKa value is 25 to 28. Source is Wikipedia. So from these we concluded that chloroform is more acidic than fluoroform. Now, so we understand the acidity. Let's come to the application of fluoroform. It's a chemical reaction. This is a brief or summary slide. We'll go this topic later. Now, so this is fluoroform. It can remove one proton and produce this trifluoromethyl anion or CF3 minus. And these can undergo nucleophilic trifluoromethylation. Why? Because these carbon has a negative charge, and that's why I can say it's nucleophile, because nucleophiles are electron rich species. So it can act as nucleophile, and through nucleophilic attack it will transfer this CF3 group. So that's why this is called nucleophilic trifluoromethylation. Not only that, student, these CF3 minus anion can eliminate one fluoride ion F minus and produce difluorocarbene or CF2. I've already discussed a dedicated lecture on this, you may visit. So this difluorocarbene is nothing but singlet carbene. Why? Because the lone pair, this p orbital is vacant, so this is vacant p orbital, and the lone pair on this fluorine atom could be delocalized into this vacant p orbital, such that the electron deficiency or electrophilicity of this carbon could be minimized. And the parent lone pair, the carbene lone pair is there in sp2 hybridized orbital. So that's why this is actually a singlet carbene. And by the way, you may consider that's a 2 carbene. This is CF2 plus this is CF2. These two can combine and it can produce a double bond or pi bond. So you can consider as a CF2 double bond CF2. This is nothing but this is tetrafluoroethylene. I've already discussed a dedicated lecture on this also, and these can undergo polymerization to produce polytetrafluoroethylene or PTFE or Teflon. This is extremely used polymer. This is chemically inert and it is used in non-stick cookware very well. I've already discussed a dedicated lecture on this also. Okay, so now in this case what happens, you may consider this step. It is actually alpha elimination of trifluoromethyl anion to produce difluorocarbene and fluoride. Because student, for alkene preparation you have learned beta elimination, but in this case alpha elimination, because this atom is eliminating from the attached carbon atom. So that's why since the same carbon, that's why it is called alpha. Now let's go to the application of nucleophilic trifluoromethylation. This part is extremely interesting. First is the reaction of this fluoroform in presence of strong base. Student, first at the beginning I told that this CH proton is moderately acidic. So if you use strong base, just imagine this will be deprotonated and instantly it can produce CF3 minus or trifluoromethyl anion. And one of the strong base is, student, KHMDS or potassium hexamethyl silyl amide. So actually these silyl amides are very strong base, because you can see two bulky trimethyl silyl groups are there, so it cannot act as nucleophile. So it is actually a non-nucleophilic base. By the way, there are many other non-nucleophilic bases like LDA, etc. I made a dedicated lecture, you may visit for further learning. So this is a very strong non-nucleophilic base, so it will produce this trifluoromethyl anion which can act as nucleophile. So in next step, it can attack this silicon center and remove this chloride. Now in this way, trimethyl means you can say trialkyl silyl trifluoromethyl derivative could be prepared. And remember students, silicon chlorine bond is not that much stable because both belongs to third row, whereas silicon carbon bond is relatively better. You may consider carbon is second row, silicon is third row, so overlap is relatively better, bond distance less, so bond is stronger. This is the story, but I would clarify that this bond is not that much stronger like silicon fluorine or silicon oxygen, because in these two case back bonding, I mean lone pair on fluorine or oxygen, could be delocalized into the vacant d orbital of silicon. So that back bonding makes these two bonds stronger. So I made a dedicated lecture on silyl ether chemistry or enolate chemistry. You can get the application of this concept there. Now, similarly, under this reaction condition, you have produced CF3 minus trifluoromethyl anion. So it can act as nucleophile and it can attack this carbonyl carbon, which is electrophilic in nature at very low temperature, because remember this KHMDS is actually a very reactive reagent. That's why low temperature and inert condition student is essential. Means inert means moisture free gas, like in moisture free inert gas like argon is needed. So from low temperature, if you bring it room temperature, reaction is completed. So in this way it produces this alcohol derivative. So you may consider nucleophilic addition to carbonyl carbon. So this is the reference. Now next reaction. Similarly student, I have explained that this amide produces this CF3 minus anion nucleophile, and it can also react with DMF. DMF is nothing but N,N-dimethyl formamide. DMF is not a good electrophile, but still it's a reversible way, it can bind and open. So this is first produced. So you can see it's nothing but a potassium salt, means this anion K plus DMF as solvent. Now if you allow it to react with aldehyde, just I have explained ketone, so you can use using same logic, you can say it could result in this alcohol derivative using aldehyde. Now if you take SX, X is actually a good leaving group like chlorine, there is SPH, etc. So these will attack on this sulfur and this X will leave, and ultimately it will produce ARSCF3. Not only that, if you react it with a star, so you can say that's a PHC double bond OMe. Then these nucleophile will attack here through acyl nucleophilic substitution type reaction. It will go and it will produce a ketone with, you can say, one side CF3 attached. It's a very unique molecule. Okay, so now, and by the way, you may have a doubt that, sir, what is this reaction? This reaction you may consider in this way, student. You have provided sulfuric acid, very strong acid, so this amine could be protonated, nitrogen. So after protonation it becomes a good leaving group, so you can expect, so in this way hydrolysis will happen, means it will produce, because it's a negative charge, excess electron, so this will leave, leaving group is neutral, so it will leave efficiently. Later on water so it will produce a carbonyl derivative. Later on water molecule will attack, so I mean CF3 C double bond OH, and formaldehyde have a tendency to form, means aldehyde have a higher tendency to form gem diol, and not only that, there is a very stronger electron withdrawing group present here, so gem diol formation tendency will be higher. So okay, fine, so it will be produced. Now, and not only that, this gem diol could further be stabilized in this way also, you can think, through hydrogen bonding. So this is CH, this is OH, this is OH, so this is a hydrogen bonding, student. So in this way these diol could be stabilized. So that could be the another driving force why this ketone prefer to remain in the diol stage. Not only that, you can remember these examples, sir, not CF3, CCl3, chloral hydrate. This aldehyde forms diol, and in that diol there is hydrogen bonding. Oh, sorry, gem diol, and then in the gem diol there is hydrogen bonding. Now, so I guess you have understand this. Next, go to the next slide. So student, this slide is very interesting. If you look at this molecule, it's a pretty interesting. Why I'm saying this molecule here, you can see that here silicon is attached to 3-methyl, and similarly this is the reagent. Now if you treat it with tetramethyl ammonium fluoride, so it's actually a salt, N plus and F minus. This F minus attacks this silicon center, and ultimately it comes back. So in this way, what it produces? It produces a silyl amide, and corresponding cation is this tetramethyl ammonium cation. Now these act as base. Just some time before I have described why it is a very strong base. So this part, and it produces trimethyl silyl fluoride leaves. I sometime before here I have explained that the silicon fluorine bond is significantly stable because of back bonding. That is the driving force for this reaction. Now in situ we have generated the base. So if you treat this with this Fluoroform DMF mixture, and if you next step, if you provide a ketone, simple addition reaction, nucleophilic addition to ketone to corresponding tertiary alcohol. So that's true. In the next step, if you provide the similar nucleophile CF3 minus to this compound, then nucleophilic attack happens here and produces here also. This is also a tertiary alcohol. So this is the reference. Now another interesting information is preparation of perfluoroalkane. Why this perfluoroalkane? Means what is this perfluoroalkane? I'll learn. Before going to that, let's learn a very easy reaction. So if you treat this fluoroform with fluorine, it produces CF4. Question, why? First of all, remember I told at the beginning that fluorine is extremely reactive, less selective. So wherever it finds any hydrogen, means CH bond, it reacts with these and produces CF4, carbon tetrafluoride. And remember student, this CF4 is more stable compared to CCl4, CBr4, CI4. I mean other tetrahalide. I made a dedicated lecture on it also, you may visit. Stronger bond. So this is the most stable, and it's true for all cases. Carbon fluorine bond is one of the strongest bond. So it produces. Similarly, if you treat this fluoroform with this is tetrafluoroethylene, addition reaction happens and produces this many fluorine or carbon containing molecule, and this is called perfluoroalkane. You may remember the story in this way that, sir, this is hydrogen, this is CF3. So one side hydrogen got attached, another side, sir, this CF3 got attached. So this you may consider it's an addition reaction on double bond. Similar way, and in this case, aluminium chlorofluoride is act as catalyst. Now you may think that, sir, why it is interesting? One of the thing I can say from the previous learning, that student, this molecule has only one proton. So I can say this is also significantly acidic, compare like this fluoroform. So you can easily prepare by using strong base. You can also prepare CF2, CF3. Now if there is no chance of beta elimination, means if you can restrict that step, so you can make this part nucleophile and you can attach this part to any organic moiety. Previously we were discussing trifluoromethyl group attachment. Right now you can attach these also. So that is the interesting point. By the way, they have another lots of interesting properties. Even if you look at this chemical, they are inert. In chemically, apart from CH bond, other things are inert. So you can look at Teflon. It's a very inert chemical. So you can cook on this. So that is the proof. Even if they are hydrophobic in nature. So lots of interesting property they have. This is the reference. Now let's go to our discussion of question. That is, if you take this reagent, trimethyl silyl chloride and BrCF3 in presence of this phosphine, what is the product? Student, Just look at here. This is a phosphorus having a lone pair of electron, and we know that phosphorus is a good nucleophile because it is softer in nature. So it can react with this BrCF3. How? Phosphorus will attack as a nucleophile and it will leave. Now you can think that, sir, it looks quite wrong, not that much convenient. Why this happened? I'll explain. So it attacks and it produces PET2N thrice with Br charge, and phosphorus will have a positive charge because it attacked with a lone pair, and it produces CF3 minus. Now question, why attack happens? If you look at this reagent, student, the polarity, this bromine is expected to be delta plus, this is delta minus. Surprise, why, sir? It is believed that the electronegativity of CF3 is lesser than fluoride, greater than chloride, and we know that chloride has more electronegativity than bromide, so directly I can say that it is more electronegative than bromide too. So consequently you can expect that, sir, after this bromine will have delta plus, so nucleophilic attack on this bromine is logical. So now in this way it produces these nucleophile or CF3 minus. So this CF3 minus will attack this silicon center and remove this Cl. Logic I have explained previously. So in this way it will produce trimethylsilyl trifluoromethyl. So this is the answer. And by the way, as a reference, you can visit this paper. I have provided the reference. Actually, I think this is a German language, so you can copy this part and you can put it in the any translating app like Google Translate, and you can read whatever is written. You can see the mechanism. So if you react this phosphine derivative with bromine, so it produces, this is attached, CF3 gone. So CF3 is outside as counter anion. This is the positive part, and later on this CF3 attack this silicon chlorine and ultimately produces this reagent. Okay, so this is the proof. So what is the answer here? Answer is option B. Now if this question given in your exam, how can you come to the right answer less than 30 seconds? First of all, you need to remember the statement of electronegativity value of this CF3, and phosphorus is nucleophilic. So where it can attack? It can attack on this bromine, produces CF3 minus anion, and anion is there, second row element, silicon will form stable bond with this, so that will be the product. And by the way, if you don't know the answer also, you can get the right answer. How? Look at the options. Silyl bromide, from where bromide will come? Okay, let's accept that you have understand wrongly, so bromide and anion will come out from the reaction mixture. Silicon bromine bond is lesser stable compared to silicon chlorine bond, because silicon is third row element, chlorine is third row element. Silicon is third row, bromine is fourth row element, so overlap even poorer. So not a genius choice. Second thing, sir, trimethylsilylamide, from where NH2 do you get? Where the nitrogen is there, sir? Here it's a solvent. And another thing, it will hydrolyze. Did I provide any workup or water source? So this is actually a dummy option, not possible. Third, sir, SiF, from where the fluorine can come? In the reaction, there could be CF3 minus. It's not like that. And there is an electrophilic center like this silicon. So this is not that much logical. Student, it's a question. But if you look at another option, wow, it's a great logic. So this is the answer. Okay, so now in conclusion, what you have learned today, that carbon fluorine bond is one of the strongest covalent bond due to proper orbital overlap of second row element and high reactive nature of this fluorine, because since the fluorine is extremely reactive, that's why the bond it forms is very stable. In haloform reaction, fluorine or hypofluorite means I haven't find its existence. If you know about it, please write in the comment box. So it cannot be used due to excessive electronegativity of the fluorine. More reactive, less selective. Remember this logic, it's enough. Now CF3 is lesser acidic than CHCl3 due to the participation of vacant d orbital of chlorine to stabilize the corresponding conjugate base using -R effect. And this CF3 anion can participate in nucleophilic trifluomethylation reaction. This is a very important strategy to introduce CF3 group inside an organic moiety. There are other methods also I shall discuss in future. Now, and finally, the electronegativity order, please remember this. Fluorine is more reactive than trifluoromethyl and electronegative than trifluoromethyl, and this trifluoromethyl is even more electronegative than chlorine. This is a very interesting property, and this is because the 3 fluorine atom attached to this carbon, that's why this carbon became extremely electron deficient or electronegative. Okay, means its tendency to grab or pull the electron density from the covalent bond is increased. That's a typical definition of electronegativity. Okay, so this is the end of discussion. I believe this video may be useful. If you really enjoy this content, please help this channel to grow. Please share among your Facebook groups. Okay, and you may visit my 2 other channels for further learning. Stay happy, stay blessed. See you in my next video. Bye bye.